Let's talk about something weird, something that might just change the way you see everything. What if I told you that the entire universe, yes, the whole thing, might be in some way alive? This isn't just wild speculation. There are actual scientists, physicists, and philosophers who argue that the universe might function like a living organism, growing, evolving, and even learning. And if that sounds crazy, well, let's just remember that at one point, people thought the sun revolved around the earth, so science has a habit of surprising us. Before we start calling the universe our cosmic overlord, let's define what it actually means to be alive. In biology, life has a few defining characteristics. It grows, it adapts, it responds to stimuli, it metabolizes energy, it reproduces, and maybe regrets its life choices at 3 a.m. Simple, right? Well, the universe does some pretty suspiciously alive things when you look closely. For example, it expands. Ever since the Big Bang, the universe has been growing, kind of like a baby that never stops getting bigger. But not just that, it evolves. The early universe was just a hot, chaotic mess of particles. Then, over billions of years, those particles formed stars, galaxies, planets, and eventually us. That's not just change. It's a structured, organized kind of change, like the way life evolves over time. In metabolism, the universe is constantly transforming energy. Stars burn fuel, black holes consume matter, and galaxies recycle elements to form new stars. It's a grand cosmic exchange where nothing is ever truly wasted. Even when stars die, they leave behind elements that become part of new planets, new solar systems, maybe even new life. Now here's where things start getting really bizarre. Some scientists have suggested that the structure of the universe looks eerily similar to the structure of a brain. Yes, your brain, the thing currently trying to process this information. Neurons, the cells in your brain that handle information, are connected by vast networks that allow them to communicate. Now, when astronomers map out the large-scale structure of the universe, the way galaxies and cosmic filaments are connected, it looks strikingly similar to those neural networks. A web of connections stretching across space, linking galaxies together, just like neurons link thoughts together in your mind. But it gets even weirder. Some researchers have argued that information itself might be a fundamental part of the universe. Just like your brain stores and processes information, the universe might be doing something similar on a cosmic scale. Could the universe be thinking? Could it have some form of awareness? We don't know. But the fact that we're even asking the question is pretty wild. Alright, here's where things take a turn from weird to full-blown mind-bending. If the universe is alive, does that mean it has a purpose? A goal? Some scientists and philosophers argue that consciousness might not just be a weird side effect of biological brains, but something woven into the very fabric of reality. This idea, known as panpsychism, suggests that consciousness didn't suddenly emerge with human brains or even with the first life forms. Instead, it has always been woven into the very fabric of existence, existing at some level in everything, from elementary particles to entire galaxies. Now, before you start imagining the universe lying on a therapist's couch, sighing, "I just feel so empty inside," let's get one thing straight. This doesn't mean the universe is a giant floating brain contemplating its own existence. Rather, it challenges our understanding of what consciousness actually is. We still don't fully understand how our own awareness works. One of the most famous theories that touch on this is integrated information theory, developed by neuroscientist Giulio Tononi. This theory suggests that consciousness arises when a system has a high degree of informational complexity and integration. So, if your brain, made up of 86 billion neurons, generates consciousness because of the way its information is connected, could the same thing be happening at a larger scale? Could the universe, with its web of galaxies, black holes, and quantum interactions, be thinking in some way? One of the most intriguing ideas comes from physicist Roger Penrose, who believes that consciousness might be connected to the world of quantum mechanics. At the quantum level, particles behave in ways that are, frankly, hard to explain without using words like spooky and mind-boggling. One of the most famous phenomena in quantum mechanics is the observer effect, which suggests that the act of measuring or observing a quantum system can change its state. Before it's observed, a particle exists in multiple possible states at once, a superposition. But the moment we measure it, it chooses a specific state. This raises unsettling questions. Is the universe, in some small way, aware of being observed? Could it be that our minds are not separate from the fabric of the cosmos, but are instead entangled with it in ways we don't yet understand? Some researchers even speculate that consciousness could be a fundamental force, just like electromagnetism or gravity, playing a role in shaping reality at a fundamental level. If this is true, then everything, from the smallest subatomic particles to entire galaxies, could possess some primitive, rudimentary form of awareness. It wouldn't be the kind of self-aware consciousness we experience as humans, but it might be something far more basic, like a faint knowing that influences the behavior of matter itself. And now, things get even stranger. Enter Robert Lanza. His theory, known as biocentrism, suggests something completely radical. Life and consciousness don't arise from the universe. The universe arises from life and consciousness. Yes, according to Lanza, space and time don't exist as objective, independent things. Instead, they're constructs that only come into existence when an observer is present. In other words, the universe doesn't exist unless there is something to perceive it. If this is true, then reality isn't some vast, cold, mechanical system that produced life as a random accident. Instead, life and consciousness are what create reality itself. No observers, no universe. This idea has some truly wild implications. For one, it suggests that before conscious beings evolved, there was no reality in any meaningful sense. That raises some awkward questions. Was the universe just sitting in some kind of cosmic waiting room for 13.8 billion years, waiting for life to show up and press the play button? If consciousness is required for reality to exist, how did the Big Bang even happen? Who or what was there to observe it? And the biggest question of all, what happens when the last observer in the universe is gone? Does reality just disappear? This is where things start sounding a bit like Schrodinger's cat, the famous thought experiment in which a cat in a box is both alive and dead until someone opens the box to check. If Lanza is right, the entire universe is like that cat, existing in some undefined state until a conscious being looks at it. And if that's true, then we are far more important than we ever imagined. We're not just tiny, insignificant specks in an unfathomably large cosmos. We are the reason it exists in the first place. Life evolves. That's kind of its thing. Tiny, single-celled organisms crawling around in ancient oceans eventually turned into dinosaurs. And those dinosaurs, at least some of them, turn into the birds that now steal your fries at the beach. Evolution is the universe's ultimate upgrade system, constantly tweaking things to survive in new environments. But what if evolution isn't just for living things? What if the entire universe is evolving? Sounds weird, right? But some physicists think that the cosmos might be following the same basic rules as natural selection, just on a much, much grander scale. Enter one of the strangest ideas in modern physics: cosmological natural selection. Let's talk about black holes. For a long time, they were seen as the ultimate dead ends. Matter and energy go in, but nothing comes out. Physicist Lee Smolin proposed that black holes might be the universe's way of reproducing. According to his theory, when a black hole forms, it could actually create a brand new universe inside it. That new universe might have slightly different physical laws than our own, just like how genetic mutations create variations in living organisms. In other words, black holes might be baby universe factories, each one spawning a whole new reality with its own version of space, time, and physics. Now, before you start imagining a bunch of tiny universes running around like cosmic toddlers, let's clarify. This process wouldn't happen inside our own universe where we could see it. Instead, the new universe would exist in a separate space-time bubble, connected to ours only through the black hole. If this is true, then universes that produce more black holes would end up making more baby universes. Over time, those universes would become more common, just like successful species on Earth outcompete weaker ones. And guess what? Our universe is very good at making black holes. There are trillions of them scattered across the cosmos, lurking in the centers of galaxies and floating around after devouring unlucky stars. If black holes really do create new universes, then we might be living in a cosmic family tree, where every universe is a descendant of a black hole in another universe. And then there's the fine-tuning problem. The physical laws of our universe seem oddly perfect for forming stars, galaxies, and ultimately life. If the laws of physics were even slightly different, atoms might not form, stars might not ignite, and we wouldn't be here to argue about pineapple on pizza. If cosmological natural selection is real, then this fine-tuning might not be a coincidence. Universes that are better at producing black holes would keep reproducing, while universes with bad physics, ones that can't make stars or black holes, would simply fizzle out. So, is the universe alive? The answer is maybe. It doesn't fit neatly into our biological definitions of life, but it does behave in ways that make us question whether those definitions are too limited. It grows, it changes, it processes information, and it might even evolve over time. At the very least, the universe is a system that behaves in ways we're only beginning to understand. And the fact that we, tiny little humans, are capable of asking these questions might just mean that the universe is alive because we are part of it. So, the next time you look up at the night sky, just remember, you might not just be looking at the universe. The universe might be looking back.
Let me ask you a question. Have you ever stared up at the night sky and wondered where it's all heading? The stars, galaxies, black holes, and even those rogue planets wandering the cosmos. What's the universe's ultimate destination? Is there some cosmic finish line, or does space just go on forever? Spoiler alert, the universe is going somewhere, but it's not exactly a smooth ride. Picture a cosmic GPS constantly rerouting itself thanks to a chaotic driver called physics. The question of where is closely tied to how the universe behaves, and it's been doing some pretty bizarre things since the Big Bang. 13.8 billion years ago, the universe decided to hit the ignition switch, and boom, the Big Bang happened. Since then, it's been expanding outward, like a loaf of raisin bread rising in the oven, except the raisins are galaxies, and this oven is everywhere. The farther away a galaxy is, the faster it's moving. That's called Hubble's law, a discovery that told us the universe is not just sitting around, it's stretching, growing bigger, and dragging everything along for the ride. Now here's where things get really interesting. Gravity, that force keeping your feet on the ground and planets in orbit, should be slowing down this cosmic expansion. But surprise! Thanks to dark energy, an invisible, mysterious force that makes up about 68% of the universe, the expansion is speeding up. Dark energy is like the universe's hyper-caffeinated personal trainer, pushing galaxies apart faster and faster. So, where are galaxies headed? In the short term, and by short we mean a few billion years, galaxies like our Milky Way are still mingling and even crashing into one another. In fact, mark your calendars. In about 4.5 billion years, we're scheduled for a front row seat to the Milky Way's epic collision with our neighboring galaxy Andromeda. But don't panic. Your descendants, or future AI overlords, will probably be fine, since stars are spaced so far apart that very few, if any, will directly collide. Beyond these localized dramas, galaxies are slowly drifting apart, and eventually, they'll be so far away from each other that even light won't be able to travel between them. Imagine going to a party and realizing everyone has left forever. That's where the universe is heading. Stars are busy burning their fuel, planets orbit peacefully most of the time, and black holes lurk ominously in the galactic centers. But nothing in the universe gets a forever pass. Stars will eventually run out of fuel and either puff up as red giants before fading as white dwarfs, or they'll go out with a bang as supernovae and leave behind neutron stars or black holes. Even black holes, those seemingly eternal cosmic vacuum cleaners, aren't forever. Thanks to a process called Hawking radiation, they slowly evaporate over trillions of years, shrinking until they simply vanish. So what's left after all that? Just a cold, empty universe filled with a sparse soup of subatomic particles, drifting aimlessly. Not exactly a postcard-worthy destination. Well, let me introduce you to a few of the wildest theories scientists have cooked up for how our universe might meet its ultimate fate. Spoiler alert, none of them involve happy endings. But hey, at least we've got a few billion or trillion years before any of these galactic finales play out, so let's dive in and enjoy the ride. Heat death, aka the Big Freeze. This scenario is currently the frontrunner in the universe-ending predictions, and honestly, it's about as exciting as waiting for paint to dry if that paint were the entire cosmos slowly cooling down to an eternal snooze. Here's how it works. The universe keeps expanding forever and ever. Galaxies drift farther apart until they're completely isolated, and all the stars burn through their fuel, flicker out, and die. Imagine the cosmic equivalent of the most deserted, silent night, where every last light bulb has gone out. Why does this happen? Dark energy, that mysterious force responsible for pushing the universe apart, keeps doing its thing without any signs of slowing down. Over time, stars will burn all their hydrogen, fuse heavier elements, and then poof, they're gone, leaving behind white dwarfs, neutron stars, or black holes. Even black holes, those seemingly eternal cosmic voids, aren't immune. They will slowly radiate energy and evaporate over a mind-bendingly long time scale. What are we left with after all this cosmic drama? Just a dark, cold universe where even atoms have broken down. No stars, no galaxies, no black holes, just a vast expanse sitting a few degrees above absolute zero. It's the cosmic equivalent of winter that never ends. No light, no heat, no Netflix, just a quiet, desolate void where time itself has nothing left to count. Now let's imagine a universe that decides expansion was just a phase and gravity comes back with a vengeance. Instead of continuing to expand forever, the universe stops, changes its mind, and begins collapsing inward, like a cosmic rubber band snapping back to its original shape. This is the big crunch, where gravity wins the tug of war against dark energy and pulls everything, galaxies, stars, planets, even space-time itself back together. Picture this. All that lovely raisin bread we use as a metaphor for the expanding universe doesn't just get stale. It gets thrown back into the mixing bowl, raisins and all. Galaxies that were once drifting peacefully apart are now on a high-speed collision course back toward each other. Stars spiral inward, black holes merge, and the universe becomes one giant gravitational mosh pit. Eventually, everything condenses into an impossibly hot, dense state, not unlike how the universe started during the Big Bang. Some theories suggest this collapse could trigger another Big Bang, essentially hitting the cosmic reset button. If true, we could be living in a never-ending cycle of bangs and crunches, a sort of infinite loop for the universe. Is that comforting or terrifying? I'll let you decide. The Big Rip, a theoretical cosmic catastrophe that turns the universe into a cosmic soap opera finale. If the Big Crunch is a dignified curtain call and heat death a slow fade into darkness, the Big Rip is the dramatic star who flips over the table and storms out of the galaxy. Here's how this chaotic cosmic scenario might play out. Imagine dark energy, the mysterious force responsible for the universe's ever-accelerating expansion, becoming overzealous. Right now, dark energy is just steadily pushing galaxies apart. But in the Big Rip scenario, it doesn't stop there, it goes rogue, amplifying its effect until it overpowers all other forces holding the universe together. Gravity, electromagnetism, even the forces binding atoms themselves. Dark energy goes on a cosmic rampage, tearing through all of it. It starts slow, deceptively calm. Galaxies, already socially distancing, drift farther apart until they're so isolated that no light can travel between them. But dark energy isn't satisfied with just making galaxies socially awkward loners. Next, it moves in on galaxy clusters, flinging them apart like celestial bowling pins. Then it gets personal, tearing individual galaxies limb from limb. Stars that were once happily orbiting in their galactic homes are tossed into the cosmic wind. But wait, it gets even more intense. Eventually, solar systems themselves unravel. Planets, moons, and asteroids are flung from their gravitational ties as the space between them stretches faster than gravity can compensate. Imagine standing on your home planet and watching your neighboring stars get yanked out of existence like a cosmic magic trick. Not exactly comforting bedtime material, right? But the universe isn't done yet. The Big Rip continues its relentless pursuit down to the most fundamental scales. Molecules break apart as the bonds between atoms fail. Then dark energy goes after the very building blocks of reality, atoms themselves. Electrons get ripped from their nuclei, protons and neutrons disintegrate, and all that's left are lonely subatomic particles drifting through a universe that has quite literally torn itself to shreds. In this scenario, time runs out in a wild crescendo of destruction. The universe doesn't just fade away, it's shredded into oblivion. What's left behind is a featureless expanse of isolated particles, floating endlessly in a void that used to be full of stars, galaxies, and wonder. So while the Big Rip is just a theory, it's definitely the most theatrical option on the menu of cosmic fates. But hey, at least it would go out with a bang, or rather billions of tiny rips echoing across the void. Here's the thing nobody knows for sure which ending we'll get. The fate of the universe hinges entirely on dark energy, that elusive force we still don't fully understand. In the grand scheme of things, the universe is heading toward a quieter, colder, lonelier place. Galaxies are drifting apart, stars will burn out, and eventually even black holes will fade into the void. It's a slow march toward cosmic silence. But despite all that, the universe is still filled with beauty, wonder, and endless stories waiting to be told. And even if everything is drifting apart, at least we can say we were part of the greatest journey ever, the story of existence itself.
Galaxies are drifting toward something we can't see. It's like the universe has a secret and a bunch of galaxy clusters are in on it, sneaking off in the same mysterious direction, far faster than expected, and completely ignoring the rest of the cosmic crowd. What could possibly be pulling them, or pushing them? This is the enigma of dark flow, a phenomenon that hints at mysteries lying outside the observable universe, tugging at the very fabric of reality. What could be out there orchestrating this celestial migration? The story of dark flow begins with the cosmic microwave background, CMB, the faint glow left over from the Big Bang, some 13.8 billion years ago. This radiation is like a snapshot of the universe in its infancy, a patchwork of tiny temperature variations that seeded the formation of galaxies and galaxy clusters. Scientists studied the CMB to understand the universe's large-scale structure, but in 2008, a team led by astronomer Alexander Kashlinsky noticed something odd while analyzing data from NASA's Wilkinson Microwave Anisotropy Probe. They were looking at the motion of galaxy clusters, massive congregations of hundreds or thousands of galaxies bound together by gravity. These clusters, some spanning millions of light years, move through space, influenced by the gravitational pull of nearby matter. But Kashlinski's team found that a large number of these clusters, scattered across billions of light years, were moving in a coordinated direction at speeds up to 1,000 kilometers per second, about 2.2 million miles per hour. This wasn't random drifting. It was as if an invisible current was pulling them toward a specific region of the sky, near the constellations Centaurus and Vela. They called this phenomenon dark flow, a nod to its mysterious nature and its resemblance to other dark puzzles like dark matter and dark energy. The term is a bit tongue-in-cheek, like naming a cosmic ghost Casper, but it captures the eerie sense that something unseen is at play. What makes dark flow so intriguing and paradoxical is that it seems to defy the uniformity of the universe. According to the standard model of cosmology, the universe should look roughly the same in all directions on the largest scales, a principle called isotropy. Yet, dark flow suggests a preferred direction, as if the universe has a cosmic exit sign pointing somewhere beyond our reach. To grasp why dark flow is such a head-scratcher, we need to understand how it was detected. The key lies in a phenomenon called the kinematic Sunyaev-Zel'dovich (KSZ) effect. When CMB photons pass through a galaxy cluster, they can scatter off hot electrons in the cluster's gas. If the cluster is moving relative to the CMB, this scattering slightly shifts the photon's energy, creating a subtle distortion in the CMB's temperature. By measuring this distortion, astronomers can infer the cluster's velocity. Kashlinski's team analyzed the KSE effect for over 1,000 galaxy clusters, using X-ray data to pinpoint their locations and WMAP data to measure the CMB distortions. The results were startling. Clusters up to 2.5 billion light-years away were moving in the same direction, toward a region roughly 150 degrees across the sky. This wasn't a small, localized effect. It spanned a significant chunk of the observable universe. To put that in perspective, if the universe were a giant beach ball, dark flow would be like noticing all the sand grains on one side sliding toward a single point. At first, some scientists hoped the explanation for this strange galactic drift might already be hiding in plain sight: the Great Attractor. This is a gravitational anomaly located in the general direction of the Centaurus and Hydra constellations, somewhere between 150 to 250 million light-years away from us. It's not a single object, but rather a region packed with galaxies, dust, and dark matter, so dense that its combined gravitational pull is dragging galaxies, including our own Milky Way, toward it at speeds around 600 kilometers per second. That sounds like a strong candidate, right? If the Great Attractor is yanking us toward it, maybe it's also responsible for the dark flow. But here's the catch: it's just not enough. For starters, the Great Attractor lies well within the observable universe and is relatively local in cosmic terms. It certainly influences nearby galactic motion, ours included, but it doesn't reach far enough. The galaxies showing signs of dark flow are located as far as 2.5 to 3 billion light-years away, and they're all moving in the same direction. That's way beyond the gravitational influence of the Great Attractor. Even if you stack the Great Attractor with its neighboring massive structures, like the Shapley supercluster, which is even more massive and sits a bit further away, you still don't get enough gravitational power to explain the observed velocities and coherence of the dark flow. These galaxies aren't just drifting, they're rushing in the same direction, across a scale that spans a significant portion of the observable universe. That level of synchronized motion isn't something we'd expect from normal local gravitational effects. Another issue is direction. The Great Attractor lies along what astronomers call the zone of avoidance, a part of the sky heavily obscured by the dust and stars of the Milky Way. That makes observing it challenging, but it also makes it easier to misinterpret what's hiding behind the galactic curtain. Over time, better data has allowed us to map out this region more clearly, and it turns out the mass there's nowhere near enough to account for the scale of the motion we see in the dark flow. So while the Great Attractor was once seen as the cosmic puppet master behind galactic motion in our region of the universe, it now looks more like a mid-level manager, important, sure, but not running the whole show. One hypothesis is that a massive concentration of matter, a supercluster of galaxies, or even a denser, exotic object, lies just beyond the observable edge, pulling clusters toward it. Picture a cosmic mountain just out of sight, its gravity luring galaxies like hikers drawn to a summit. To cause dark flow, this structure would need to be enormous, dwarfing anything within our observable universe. For context, the largest known structure, the Hercules Corona Borealis Great Wall, spans about 10 billion light-years and contains countless galaxies. The dark flow source would need to be even grander. Another idea involves the multiverse, a speculative concept where our universe is one of many bubbles in a larger cosmic foam. If another universe or a massive object in a neighboring bubble is close enough, its gravity could leak into our universe, creating dark flow. This is a bit like imagining your neighbor's music vibrating through your walls, except the neighbor is another reality. While this idea is scientifically provocative, it's hard to test, as the multiverse remains theoretical. A less exotic explanation is that dark flow is a relic of the early universe. During cosmic inflation, a rapid expansion just after the Big Bang, quantum fluctuations could have created uneven patches of matter. If one such patch was particularly dense, it might still influence galaxy clusters today, creating a directional pull. This would mean dark flow is a fossil of the universe's chaotic birth, preserved like a footprint in cosmic mud. Not everyone's convinced. The idea of the dark flow sparked a lot of debate. Some scientists argue the data might be a statistical fluke. The WMAP data, while groundbreaking, had limitations in resolution and sensitivity. Some astronomers argued that the signal Kashlinski's team detected could be noise masquerading as a cosmic current. To test this, researchers turned to the Planck satellite, which provided higher resolution CMB data. In 2013, Planck's results cast doubt on dark flow, finding no clear evidence of coordinated cluster motion. It was like searching for a ghost and finding only shadows. But the story didn't end there. Kashlinski and others refined their analysis, using newer data and larger samples of clusters. In 2016, they reported that dark flow persisted in some datasets, though the signal was weaker than before. The debate remains open, with some studies supporting dark flow and others dismissing it as an artifact. It's a bit like arguing over whether a faint smudge on a telescope lens is a distant galaxy or just a speck of dust, except the stakes are the very structure of the cosmos. There's another possibility, that the dark flow is hinting at something wrong with how we understand the universe at large. The standard model of cosmology, known as lambda cold dark matter, assumes the universe is isotropic and homogeneous on large scales. That means it should look roughly the same in every direction, and matter should be evenly spread out. But if the dark flow is real, it breaks that assumption. It suggests a preferred direction in the universe, a cosmic bias of sorts. That would be like discovering Earth's gravity works slightly stronger in one direction. You'd have to rethink some core ideas. It could also suggest that dark energy, the mysterious force speeding up the expansion of a universe, isn't uniform. Or that our models of gravity, based on Einstein's general relativity, need some tweaking when applied across vast cosmic distances. None of these ideas are easy pills to swallow, but science has a history of swallowing the tough ones. Remember, once upon a time we thought Earth was the center of the universe. We got over it. To fully appreciate dark flow, we need to place it in the broader context of cosmology. The universe's large-scale structure is a web of galaxies, clusters, and superclusters, threaded by filaments of dark matter and separated by vast voids. This cosmic web, formed over billions of years as gravity sculpted the universe from the CMB's initial fluctuations. Dark flow, if real, suggests an external influence on this web, like an unseen hand tugging at its edges. Consider the analogy of a river. On small scales, water swirls and eddies around rocks and bends, much like galaxies move under local gravitational pulls. But dark flow is like discovering that the entire river is sloping toward an unseen ocean. This challenges our assumption that the cosmic web is self-contained, with no external forces at play. It raises questions about the universe's boundaries and what lies beyond them. Let's say the dark flow is real. That means something massive exists beyond the limits of our observable universe. It could be a massive structure, a colossal clump of matter left over from a pre-inflationary state, or even an entirely different universe with its own gravitational pull. The scale of such a thing would be unimaginable, tens or hundreds of times more massive than anything we've observed. And yet, it wouldn't be visible because its light simply hasn't had enough time to reach us. That's the poetic part of the dark flow. We're possibly being pulled by something we will never see. It's like the universe is whispering, "You're not alone." You might be thinking, okay, galaxies are drifting. Why should I care? Well, here's why it matters. If the dark flow is real, it could be our first piece of observational evidence for what lies beyond our cosmic limits. It would shake up cosmology, challenge the standard model, and force us to rethink everything we know about the universe's structure. It would also open the door to the multiverse, not just as a mathematical concept, but as something we can indirectly observe. Think about that. For the first time in human history, we might have evidence that our universe is just one of many, that the cosmos is far vaster and stranger than we've ever imagined, and that our everything is just a small corner of something far greater. That's a pretty big deal. In the end, the dark flow is about more than galaxies behaving badly. It's about the limits of human knowledge. We're standing on a cosmic island, staring out at the ocean, and we've found signs, drifting boats, strange tides that tell us something massive is out there in the fog. We just don't know what. It's humbling, it's frustrating, and it's kind of amazing. The universe has a problem. We know how much stuff should be there, but nearly half of it is nowhere to be found. Imagine you're baking a cake, and the recipe calls for a precise amount of flour. Let's say the stuff that makes up stars, planets, and even you. You measure it out, mix it in, but when the cake comes out of the oven, half the flour is gone. Poof, vanished. That's the missing baryon problem in a nutshell. The universe's recipe says there should be a certain amount of normal matter, out there, but we can only find about half of it. Where's the rest hiding? This isn't just an accounting error. It's one of the biggest puzzles in modern cosmology, and it's been keeping scientists up at night for decades. To get a grip on this problem, we need to start with the basics, baryons. These aren't some exotic space critters. They're the building blocks of the stuff we see around us. Baryons are particles like protons and neutrons, made of smaller bits called quarks, glued together by the strong nuclear force. Think of them as the cosmic Lego bricks that form atoms, which then clump together to make stars, planets, galaxies, and even that weird mold growing on your leftover pizza. Baryons are what we call normal matter, as opposed to dark matter or dark energy, which are whole other cans of worms we won't open today. Scientists have a pretty good idea of how many baryons should exist in the universe. This number comes from two key sources. First, there's the Big Bang, which left behind a predictable amount of light elements like hydrogen and helium. By studying the ratios of these elements, through a process called Big Bang nucleosynthesis, physicists can calculate how much baryonic matter was produced in the universe's fiery infancy. Second, we have the cosmic microwave background, the faint glow from the Big Bang that's like the universe's baby picture. The CMB's tiny temperature fluctuations tell us about the density of baryons back when the universe was just 380,000 years old. Both methods agree. There's a specific amount of baryonic matter out there, and it's not negotiable. In total, the observable universe is expected to contain about 10 raised to power 53 kilograms of baryonic matter. That's a 1 followed by 53 zeros. This staggering amount includes all the ordinary matter made of protons and neutrons, stars, planets, gas, dust, and everything in between. So how do we know if we're actually seeing all that matter? That's where the detective work begins. Astronomers have spent decades tallying up every source of baryons they can find. Stars are the easiest to spot. They shine brightly across the universe and reveal their mass through their light and motion. Planets, moons, and asteroids add a little more, but they're basically pocket change in cosmic terms. Then there's the gas and dust inside galaxies, which show up in radio, infrared, and X-ray wavelengths. All of this makes up the baryons within galaxies. But galaxies are just part of the story. The space between them, the intergalactic medium, is filled with thin, almost invisible gas. We can detect this elusive material when it absorbs light from distant quasars, producing faint absorption lines that act like fingerprints. There's also hot gas in galaxy clusters, heated to millions of degrees and glowing in X-rays. Add it all together, stars, dust, interstellar and intergalactic gas, and it only accounts for about half the baryons predicted by theory. That's the mystery. Half of the universe's ordinary matter was missing. Not dark matter, not anything exotic, just normal protons and neutrons that we know should exist. You might be thinking, so what? Maybe we just miscounted. But this isn't a trivial oopsie. The missing baryon problem challenges our understanding of how the universe works. If we can't account for all the normal matter, it raises questions about our models of cosmology, galaxy formation, and even gravity itself. It's like trying to balance your budget when half your paycheck is gone missing. You start doubting the whole system. Plus, baryons play a starring role in the universe's story. They fuel star formation, drive chemical evolution, and make life possible. If we don't know where they are, we're missing a big piece of the cosmic puzzle. There's also a deeper issue. The universe is supposed to be consistent. The amount of baryons predicted by the Big Bang and the CMB should match what we see today. If it doesn't, either our observations are off, or something weird happened as the universe evolved. Now for the fun part. Where's the missing half? One leading suspect is the warm-hot intergalactic medium, or WIM for short. This is gas that's not cold enough to form stars, not hot enough to glow brightly in X-rays, but just right. Think Goldilocks with a PhD in astrophysics. The WIM is thought to live in vast, filamentary structures that connect galaxies, like the cosmic equivalent of highways linking cities. These filaments are part of the universe's large-scale structure, a web of matter sculpted by gravity over billions of years. The problem is, the WIM is maddeningly hard to detect. It's diffuse, spread out over enormous distances, and doesn't emit much light. It's like trying to find a cloud of steam in a foggy bathroom. But there's hope. Some clever astronomers have spotted hints of the WIM by looking for specific absorption lines in the spectra of distant objects, like oxygen ions that signal hot gas. Others have used X-ray telescopes to catch faint glows from these filaments. The catch? These detections only account for a fraction of the missing baryons. The WIM might be a big piece of the puzzle, but it's not the whole picture. Another possibility is that the baryons are hiding in plain sight, but in forms we haven't fully accounted for. Maybe there's more gas in the outskirts of galaxies than we thought, lurking in halos that are tough to observe. Or perhaps they're tied up in faint, low-mass stars or dead stellar remnants like white dwarfs, which don't shine brightly enough to notice. There's even a wild card. Could some baryons be locked away in exotic states, like dense clumps of gas that haven't formed stars? These ideas are less popular, but they're not off the table. Let's say we do find the missing baryons, maybe in the WIM, maybe somewhere else. What then? For one, it'd be a huge win for cosmology. It'd confirm our models of the Big Bang and the universe's evolution, giving us confidence that we're on the right track. It'd also teach us more about how galaxies form and interact, since baryons are the raw material for stars and planets. And who knows, maybe we'd learn something new about the universe's structure, like discovering a hidden room in a house you thought you knew. But there's a flip side. If we don't find them, or if we find something unexpected, it could shake things up. Maybe our understanding of the Big Bang is off, or maybe gravity behaves differently on cosmic scales. That'd be a headache, but also exciting. Science thrives on surprises, and the missing baryon problem is a reminder that the universe doesn't owe us easy answers.
Let's do a little mental exercise. Imagine trying to picture a time before time. That's like attempting to visualize the color zero or hearing silence from a black hole's perspective. It's a tough one, but stick with me. The Big Bang, the point where space, time, and everything we know about the universe sprang into existence, was a pretty big deal. It's like the universe's own personal kickoff party. But what about the stuff that came before the big shindig? Was the universe hanging out in some kind of cosmic waiting room? Were there bouncers, and if so, were they made of dark matter? And did we miss the VIP entrance because we didn't get the memo? Well, here's the thing. Scientists are still trying to figure it out, and so far there's no definitive answer. But let's explore what we do know, and sprinkle in some imagination for good measure. We've all heard about the Big Bang, that epic explosion that gave birth to everything we know. Stars, galaxies, even the internet, which I'm sure you're very attached to. But it wasn't an explosion in the traditional sense. Imagine a balloon that's expanding and getting bigger, but it's not blowing up from one central point. The entire balloon is stretching, and it's not just space, it's space itself that's growing. So there wasn't a before in the conventional sense, at least not in the way we understand time. It's as if the whole concept of before didn't exist. The moment the Big Bang happened, it essentially created time. So, what was there before time? The idea of before the Big Bang is a bit tricky because, well, time itself didn't exist. The concept of time is woven into the fabric of space, and when space itself didn't exist, neither did time. Now that's a head-scratcher, right? You're basically asking, what's on the other side of nothing? Well, the truth is, we don't exactly know. It's like asking someone what they ate for breakfast before they even existed. It's a question that might not have a meaningful answer. However, a popular theory about what could have been before the Big Bang involves something called the cosmic singularity. This is the idea that all the energy and matter that would eventually form the universe were crammed into an infinitesimally small point, smaller than the head of a pin or even smaller than a grain of sand. Now, don't think of this singularity as an ordinary thing. It's not like the corner of your local coffee shop, sitting there waiting for you to swing by. It was a tiny, dense, and mind-bogglingly hot speck that packed more energy into it than your smartphone will ever know, which, as we all know, is quite a lot. And this point contained everything, and yet it didn't have any physical space or structure to it. Talk about cosmic claustrophobia. Eventually, this tiny, energy-packed speck exploded outwards and expanded into the universe we know today. Okay, so no time existed before the Big Bang. Got it. But wait, there's more. Some theorists are throwing a wild party with a theory that our Big Bang might not be the first one, but simply the latest in an ongoing cosmic cycle. This is known as the cyclic model, where the universe goes through endless cycles of birth, death, and rebirth. Picture the universe as this gigantic, infinitely repeating loop, a cosmic blender that whirs, creates a new smoothie, or Big Bang, and then resets for another round. After each Big Bang, the universe expands, evolves, and eventually collapses in on itself, only to explode again and start fresh. It's like your computer restarting after every software update, but on an epic scale that makes your annual spring cleaning look like a mild dusting. The idea here is that the universe doesn't have a definitive beginning or end. It's just one big, eternal cycle, like an infinite cosmic laundry day. Now, let's crank the weirdness up a notch. Some scientists are getting truly adventurous by proposing the idea of parallel universes. That means our Big Bang might not be the only one in town. There could be other universes out there, each with its own Big Bangs, running on its own set of rules. These universes could have entirely different physical laws, and they might even exist in dimensions beyond our understanding. Imagine that before our universe was born, there were other universes, each with their own versions of before and after. If this is true, the multiverse concept would be like a cosmic buffet, with each universe serving up its own unique reality, full of mysteries and possibilities that we can't even begin to comprehend. It's like a giant mind-bending game of choose your own adventure, except there's an infinite number of books to flip through, each with their own chapters of existence. The implications of this idea are staggering. If multiple universes are real, they could potentially overlap, collide, or even interact with one another in ways we can't detect. Some theorists have suggested that these parallel universes might share certain properties with ours, leading to cosmic accidents where universes bump into each other, triggering entirely new Big Bangs, or creating ripples that we might never notice. It's a bit like trying to figure out what's happening at a party when you can only hear the music from the next room. But who knows? Maybe those next-door universes are cranking up the jams in their own way, having their own Big Bang dance parties. We just can't see or hear them. Now let's talk about quantum fluctuations, which are the universe's way of saying, hey, let's throw a little randomness into the mix. On the tiniest scales, the universe is a chaotic, jittery place. Even in a perfect vacuum, which sounds peaceful but isn't, subatomic particles are constantly popping in and out of existence. It's like cosmic popping candy, but with way more potential for universe making. These quantum fluctuations could be the spark that triggered the Big Bang. Maybe there was a tiny little fluctuation in the quantum field that suddenly created a whole universe, kind of like shaking a soda can and hoping the fizz turns into a galaxy. And while that sounds like a long shot, quantum mechanics isn't exactly known for playing by the rules. Let's revisit the idea of nothing before the Big Bang that became everything. Now, we tend to think of nothing as empty space, nothing at all. But in quantum physics, nothing can actually be a bit more complicated. It could be a bubbling cauldron of potential energy, ready to burst into something else at any moment. So, while it might seem like nothing existed before the Big Bang, it's possible that a something, perhaps a quantum field or a potentiality, was already there, just waiting for the right conditions to explode into the universe we now know. Imagine it like a pot of soup on the stove. Sure, it looks empty, but it's full of ingredients, just waiting to boil over. That could be the best description of the universe before it began, an empty pot full of potential, just waiting for the heat to turn up. Once the Big Bang kicked off, things got really crazy. We're talking about a universe that was hotter than the surface of the sun, expanding faster than anything we could even imagine. And for the first few moments, the universe was a wild, chaotic place filled with intense energy, quarks, gluons, and photons, basically, the building blocks of everything. But if we try to look back to the actual moment of the Big Bang, we hit a wall. The laws of physics break down in the face of such extreme conditions. It's like trying to read a book when the pages keep rewriting themselves every second. The first fraction of a second after the Big Bang is still one of the greatest mysteries in modern cosmology. It's a cosmic blind spot, a time when we can't even use our best tools to figure out what happened. And that, my friends, is a bit frustrating. The big question, will we ever know? While we've made huge strides in understanding the origins of the universe, the question of what was before the Big Bang might remain just that, a question. And the answer might always be beyond our reach. Maybe the concept of before is fundamentally flawed when it comes to the origins of the universe. Maybe time itself had no beginning, and the Big Bang was just one part of an infinite cycle. Or perhaps, as some philosophers and scientists speculate, the universe has no true beginning or end, it just is, in a state of eternal flux. So what was the world like before the Big Bang? Well, the short answer is, we don't know, but that's okay, because the mystery of the universe's origins is exactly what makes it so endlessly fascinating. And who knows, maybe someday we'll crack the code and discover that the universe's before is just as mind-blowing as the universe itself. Let's take a step back and look at the universe, the vast, intricate, and astonishingly well-ordered cosmos that we find ourselves in. From the smallest subatomic particles to the largest galactic structures, everything seems to follow precise mathematical rules, governed by laws that make life not just possible, but inevitable. But why? Why is the universe so remarkably fine-tuned for life? Why do the fundamental constants of nature numbers that could, in theory, have taken any value happen to be just right for stars to form, planets to exist, and for us to be here asking these questions? Is this extraordinary order a product of random chance, an inevitable consequence of physics, or could it suggest the work of a creator? We must see what makes the universe so perfect, and whether this perfection points to a deeper design. At the heart of this mystery is something called fine-tuning. This refers to the idea that the fundamental physical constants of the universe, the strength of gravity, the charge of an electron, the mass of a proton, and many others are set at values that allow complex structures like galaxies, stars, planets, and ultimately life to exist. These numbers are not arbitrary. If they were even slightly different, the universe would be radically different, and not in a way that allows intelligent beings to contemplate it. Let's look at a few crucial examples of this fine-tuning. Imagine if gravity were just a tiny bit stronger. In such a universe, stars would burn through their fuel too quickly, collapsing before they could create the heavier elements needed for planets and life. On the other hand, if gravity were weaker, stars might never ignite in the first place, leaving a cold, lifeless universe. Yet somehow, gravity is balanced just right, allowing stars to form, burn for billions of years, and seed the cosmos with the elements necessary for life. The electromagnetic force is responsible for holding atoms together. If it were just slightly stronger, electrons would be trapped too tightly around atomic nuclei, making chemical reactions nearly impossible. If it were weaker, atoms wouldn't hold together properly, making complex molecules and, by extension, life impossible. Yet, the force is exactly what it needs to be for atoms to form stable molecules, which in turn create everything from water to DNA. Perhaps the most staggering example of fine-tuning comes from dark energy, represented by the cosmological constant. This mysterious force is responsible for the accelerated expansion of the universe. The problem? The value of this constant appears to be fine-tuned to an almost incomprehensible degree. If it were even slightly larger, the universe would have expanded too quickly for galaxies to form. If it were smaller, gravity would have overwhelmed it, leading to a collapse long before stars and planets had the chance to develop. In short, this number is so precisely set that even the smallest change would have resulted in a lifeless void. So what does all this fine-tuning mean? There are a few ways scientists and philosophers attempt to explain it. One possibility is that we just got lucky. Out of all the possible ways a universe could have formed, we happen to get one where the constants are set in just the right way for life to emerge. But this explanation is unsatisfying. The odds of all these constants aligning perfectly are astronomically small. So small that many scientists find it hard to believe that pure chance could be the reason. Another explanation is that there is not just one universe, but an infinite number of universes, each with different physical constants. This idea, known as the multiverse theory, suggests that while most of these universes would be lifeless, at least one ours happened to get the right conditions for life. If the multiverse exists, then the fine-tuning of our universe wouldn't be a mystery at all. In a vast enough collection of universes, some universe would have to turn out just right for life, and we just happen to be in that one. It's like rolling a trillion dice somewhere. At least one of them is going to land on all sixes. But there's a catch. We have no direct evidence that other universes exist. Right now, the multiverse remains a speculative idea, rather than a confirmed scientific theory. And even if it's true, it doesn't necessarily explain why any universe exists in the first place. Another explanation is that the universe is the way it is because it had to be. According to this view, the conditions we see are not the result of random chance, but rather a consequence of deeper physical principles we don't yet fully understand. Some scientists believe that certain fundamental laws make life-friendly universes an unavoidable outcome. In this view, our universe isn't an accident. It's simply following a deeper set of rules. If we understood those rules fully, we might find that a universe capable of sustaining life was always bound to happen. But this explanation just shifts the question. If the laws of physics inevitably lead to a life-friendly universe, then why do those laws exist? Why do they take the precise form that they do? Many people see fine-tuning as evidence of a creator. The idea is simple. If the universe looks like it was designed with purpose, maybe it was. The precise physical constants, the elegance of mathematical laws, and the emergence of conscious beings all suggest, to some, the hand of an intelligent designer. Every religion supports the idea that the universe was intentionally created by God. Let's see what the major religious texts say about the origins of the universe and its fine-tuning. In Islam, the Quran repeatedly points to the order of the universe as a sign of God's existence and power. Quran, chapter 21, verse 16. And we did not create the heaven and the earth and that between them in play. And the heaven we constructed with strength, and indeed, we are expander. You will not find in the creation of the most merciful any inconsistency. So return your vision to the sky. Do you see any breaks? Then return your vision twice again. Your vision will return to you humbled while it is fatigued. The Bible, particularly in the books of Genesis and Psalms, speaks of a universe brought into existence by God's will. In the beginning, God created the heavens and the earth. The heavens declare the glory of God. The skies proclaim the work of his hands. For this is what the Lord says, He who created the heavens, He is God. He who fashioned and made the earth, He founded it. He did not create it to be empty, but formed it to be inhabited. In Judaism, the Hebrew Bible, Tanakh, and other Jewish texts emphasize the orderliness of creation. The Lord by wisdom founded the earth. By understanding, He established the heavens. He established the earth upon its foundations so that it will never totter forever and ever. These ancient texts describe the state of the universe before creation in ways that strikingly align with modern cosmology. Long before scientists proposed the Big Bang Theory, Scriptures spoke of a time when the heavens and the earth were once a single entity, a unified mass, before being separated. In the Quran it is written, "Have those who disbelieved not considered that the heavens and the earth were a joined entity, and we separated them and made from water every living thing? Then will they not believe?" And then, describing the early state of the universe, the Quran says, "Then he directed himself to the heaven while it was smoke and said to it and to the earth, 'Come willingly or unwillingly.' They both said, 'We come willingly.'" Similarly, in the book of Genesis, we find this description of creation's earliest moments. "Now the earth was formless and empty, darkness was over the surface of the deep, and the Spirit of God was hovering over the waters." If we accept the idea that the universe was created, a natural follow-up question arises. Who created the Creator? Many religious traditions respond by arguing that God exists outside of time and space, meaning he does not require a cause. Unlike physical objects that are bound by the laws of nature, God is considered the necessary, self-existent being. In Islamic theology, this concept is captured in Surah Al-Ikhlas. He neither begets nor is born, nor is there to him any equivalent. Similarly, in Christian theology, God is described as eternal. "I am the Alpha and the Omega, the beginning and the end." So, can science answer this question? Science is excellent at describing how things happen, but it struggles when it comes to explaining why they happen. The laws of physics can tell us how the universe behaves, but they do not necessarily explain why those laws exist in the first place. At the end of the day, we have a universe that continues to surprise us, a cosmos that invites us to explore its mysteries, and a mind capable of asking these very questions. Perhaps the journey of understanding is just as important as the answers themselves.
Right after the Big Bang, the universe was not filled with stars and galaxies. In fact, it wasn't even filled with atoms. Instead, it was an unimaginably hot and dense sea of energy. At this stage, temperatures were trillions of degrees, and everything was so compressed that even fundamental forces like gravity, electromagnetism, and nuclear forces were unified into a single force. As the universe expanded, it began to cool. Within a fraction of a second, this cooling allowed energy to transform into matter and antimatter in the form of elementary particles, quarks, electrons, and their antimatter counterparts. However, there was a slight imbalance. For every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny extra bit of matter, the 1 in a billion difference, was enough to eventually form all the stars, planets, and galaxies we see today. In the first few 100,000 years after the Big Bang, the universe was an extremely hot and dense plasma, a chaotic mix of charged particles, protons, neutrons, and free electrons. It was so hot that atoms couldn't exist yet because electrons were constantly getting knocked away from protons and neutrons due to the intense energy. Light in this era couldn't travel freely. Every time light tried to move, it would immediately collide with a free electron, scattering in a different direction. This constant interaction made the universe opaque, like a thick fog where light was trapped and couldn't go anywhere. Around 380,000 years after the Big Bang, the universe had expanded and cooled down to about 3,000 Kelvin. This cooling was crucial because it finally allowed protons and neutrons to capture electrons and form stable, neutral atoms, mainly hydrogen and helium. This process is called recombination, even though it was actually the first time atoms were forming. With electrons now bound to atoms, they were no longer free to scatter light everywhere. With fewer free electrons to interfere with photons, light could finally travel freely through space. The universe, once a dense fog, suddenly became transparent. The light released at this moment is what we now observe as the cosmic microwave background radiation, the faint glow of the early universe that still exists today. This radiation has been traveling for over 13.8 billion years, carrying information about the conditions of the young universe. So, in short, the universe cooled, atoms formed, light escaped, and the universe became visible for the first time. While light could now move freely, there were no stars or galaxies yet. Only vast clouds of neutral hydrogen and helium gas spread throughout the universe. With no significant sources of light, the universe entered a period called the Dark Ages, which lasted for millions of years. Even though everything looked dark and empty, gravity was still at work. The universe wasn't perfectly uniform. Some areas had slightly more matter than others. These tiny differences in density, left over from the Big Bang, caused certain regions to have a little more gravity than their surroundings. Over millions of years, gravity pulled gas together into clumps, forming denser regions. As these clumps grew bigger, their gravitational pull got stronger, attracting even more matter. This process continued, forming the first cosmic structures, the seeds of future stars and galaxies. As these clumps of hydrogen and helium collapsed under their own gravity, they heated up due to the pressure. Eventually, the temperature and pressure inside these collapsing gas clouds became high enough to trigger nuclear fusion, the process that powers stars. This moment was a game changer. The first stars ignited, marking the end of the Dark Ages. These first stars, known as population 3 stars, were very different from the stars we see today. They were much larger than our sun. Some were hundreds of times more massive. They burned much hotter and shone brighter. Because they were so massive, they had short lifespans, lasting only a few million years before exploding as supernovae. When the first stars formed, they were not alone in empty space. Instead, their strong gravitational pull attracted surrounding hydrogen and helium gas, as well as other newly formed stars, creating clusters of stars. Over time, these clusters merged together, forming the first galaxies. However, these early galaxies looked very different from the ones we see today. They were small, chaotic, and misshapen. Because of abundant gas, they produced new stars at a fast rate. Over billions of years, these small galaxies collided and merged, gradually evolving into the larger, more structured galaxies we see today, such as spiral galaxies like the Milky Way and elliptical galaxies. As galaxies started forming, they didn't stay isolated. Instead, gravity pulled them together into groups called galaxy clusters. These clusters contain hundreds or even thousands of galaxies, all bound together by their gravitational pull. Matter in the universe didn't just gather randomly. Instead, galaxies and galaxy clusters lined up along vast, invisible filaments of gas and dark matter. This web-like pattern is called the cosmic web, and it defines the large-scale structure of the universe. Between the filaments of the cosmic web, there are enormous empty regions called cosmic voids. These are areas where almost no galaxies exist, just vast empty space. Some of these voids are hundreds of millions of light years across, making them some of the biggest structures in the universe. Now, let's see how planets and our solar system came into being. Stars generate energy through a process called nuclear fusion. This means they combine lighter elements to form heavier ones inside their cores. Small stars, like our sun, fuse hydrogen into helium. Larger stars can fuse helium into carbon, oxygen, and neon. The most massive stars continue fusion, forming silicon, sulfur, and iron. But there's a limit. Iron is the heaviest element that a star can create through fusion, because creating heavier elements requires more energy than it produces. This marks the beginning of a star's death. When a massive star runs out of fuel, it collapses under its own gravity, leading to a supernova explosion. These explosions are among the most powerful events in the universe. In just seconds, temperatures and pressures become extreme enough to create elements heavier than iron, such as gold, silver, and uranium. The explosion then scatters all these newly formed elements into space, enriching the surrounding gas and dust. This cycle of star birth and death repeated over billions of years, increasing the universe's chemical diversity and making it possible for rocky planets like Earth to form. About 4.6 billion years ago, one of these enriched clouds of gas and dust in the Milky Way galaxy began to collapse under gravity. This cloud, called the Solar Nebula, may have been disturbed by a nearby supernova explosion, which sent shock waves through space. As the cloud collapsed, it spun faster and flattened into a rotating disk of gas and dust. At the center, pressure and temperature increased until nuclear fusion ignited. This was the birth of our sun. While the sun formed at the center, the remaining material in the rotating disk began clumping together due to gravity and collisions. Tiny dust grains stuck together due to electrostatic forces. These grains formed small rocks, which then combined into larger bodies called planetesimals. Over millions of years, planetesimals collided and merged, eventually forming planets, moons, asteroids, and comets. Earth formed in a special region of the solar system called the habitable zone, the area where temperatures allow liquid water to exist. Being at the right distance from the sun meant Earth could develop oceans and a stable atmosphere, two key ingredients for life. Over time, geological processes shaped Earth's surface, and chemical reactions led to the formation of organic molecules, setting the stage for life to emerge. In short, we are literally made of stardust, and the same cosmic processes that created Earth also created everything we see around us. I need to let you in on a little secret. You know stars, right? Those giant, glowing nuclear furnaces that light up the universe, cook up the elements we're made of, and have dramatic deaths worthy of space opera. Yes, stars. Turns out, not every ball of gas in space gets to be a star. Some of them try, they really do, but they just don't have what it takes. Ladies and gentlemen, I present to you the brown dwarf, the moody teenagers of the universe. Not quite a star, not quite a planet, just hanging out in the cosmic friend zone, forever in between. Let's break this down. What are these brown dwarfs? How do they form? And why do astronomers care so much about them? To understand brown dwarfs, we have to talk about what makes a star a star. A star forms when a big cloud of gas collapses under its own gravity. As it shrinks, the core gets hotter and denser. And if there's enough mass, about 75 times the mass of Jupiter, the pressure and temperature reach the point where nuclear fusion can ignite. Hydrogen atoms start slamming into each other to form helium, releasing a mind-boggling amount of energy. Congratulations, you've got a star, but what if you don't quite have 75 Jupiter masses? What if you only manage, say, 60 or 50 or, bless your heart, 20? Well, my friend, in that case, you've got yourself a brown dwarf. Brown dwarfs form the same way stars do. They tried. They really did. They gathered gas. They collapsed. They heated up, but not enough. They fell short of the mass needed to ignite full-fledged hydrogen fusion, leaving them stuck in a permanent state of almost. And here's a fun twist. Some brown dwarfs might form like planets, condensing in disks around young stars. But they're the overzealous interns who accidentally outgrow their boss. Imagine Jupiter hitting the gym, bulking up to 80 times its size, and still getting told, sorry, you're not star material. You might assume brown dwarfs are, well, brown, but actually they're not. They can be red, orange, or even magenta, but astronomers are famously bad at naming things, so brown dwarf it is. Fun fact, the name was originally suggested by astronomer Jill Tarter, who later became the inspiration for Jodie Foster's character in Contact. The reason they look the way they do comes down to their temperature. Real stars, like our sun, are blazing hot and glow with a bright white-yellow light. Brown dwarfs, on the other hand, are much cooler. Think thousands of degrees instead of millions. That means their light is mostly in the infrared, which is invisible to human eyes. If you could see an infrared, brown dwarfs would be glowing like little cosmic embers. Then there's the wind. Studies suggest that wind speeds on brown dwarfs can reach thousands of kilometers per hour, strong enough to whip entire storms across their surfaces in a matter of hours. Speaking of storms, brown dwarfs have them on a truly epic scale. Some of these storms are larger than Earth itself and can persist for years, constantly churning and evolving. Observations in infrared have revealed complex, ever-shifting weather patterns, making these objects some of the most dynamic in the cosmos. And let's not forget the rain, except instead of water, we're talking about liquid iron and molten silicates. That's right. Imagine a world where scorching hot metal condenses in the upper atmosphere, forming droplets that fall as searing, fiery rain. In some brown dwarfs, temperatures are just right for this molten material to evaporate, rise into the atmosphere, and then rain down again in an endless, infernal cycle. A question: could brown dwarfs have planets? Absolutely. Just because brown dwarfs are failed stars doesn't mean they have to be lonely. In fact, many brown dwarfs have been found with their own planetary companions, proving that even stellar underachievers can have a little cosmic entourage. Now, you might be wondering, how does a planet even form around a brown dwarf? Well, the process is quite similar to how planets form around regular stars. After a brown dwarf is born, there's often a leftover disk of gas and dust swirling around it. If conditions are just right, that material starts clumping together, forming planets. Some of these planets might be gas giants like Jupiter, while others could be rocky worlds, possibly even resembling Earth. One of the most famous planetary systems around a brown dwarf is this, a young brown dwarf about 450 light years away that has a massive planet orbiting it. Then there's this one, a free-floating planet that scientists believe may have originally formed around a brown dwarf before getting kicked out into the galaxy. And let's not forget the TRAPPIST-1 system. While its host is a very low-mass star, it teeters on the edge of being a brown dwarf, proving that tiny, dim celestial objects can still have planets. But here's where things get really weird. Because brown dwarfs are still warm from their formation, they can actually keep their planets warm too, at least for a while. This means that some planets orbiting brown dwarfs could have liquid water for a few 100 million years before their host cools too much. Not exactly the best long-term investment for habitability, but hey, life moves fast in the universe. So what happens to these cosmic misfits? Unlike stars, which eventually explode or fade into white dwarfs, brown dwarfs don't really do much. Since brown dwarfs don't have a steady energy source like stars, they just cool off forever. Over trillions of years, They'll fade into the cold darkness of the universe, eventually becoming black dwarfs, completely invisible, radiating no heat, just drifting endlessly through space. Of course, the universe isn't old enough for any black dwarfs to exist yet. The oldest ones we found are still glowing faintly in infrared. We'd have to wait trillions of years to see one. And frankly, that's a bit outside our patience level. So, in a way, brown dwarfs have a last laugh. They may have failed as stars, but they're outliving most of the bright, flashy ones. So the next time you look up at the night sky, remember that among all those bright stars, there are countless failed stars out there too, lurking in the darkness, waiting for their moment of recognition. Brown dwarfs may not shine like the sun, but in their own way, they're just as fascinating, and they've got one heck of a story to tell. Oh, and if you're wondering when scientists discovered the first brown dwarf, that honor goes to the mid-1990s. In 1995, astronomers confirmed the existence of Tide 1, a brown dwarf located in the Pleiades star cluster. Since then, we've found many more, revealing just how common these celestial underachievers really are.
Have you ever wondered how black holes, the gravity-powered monsters, come into being? How does the universe take something as peaceful as a star and turn it into a ravenous void? Let's be real, a black hole is basically a star that said, you know what, I'm done being the center of attention. Time to suck the fun out of everything instead. But not all stars are destined to become black holes. The universe doesn't just hand out black hole badges to any old ball of gas. To qualify, a star must be massive, at least 20 times the mass of our sun. Let's call this star Bob. Bob spends most of his life peacefully fusing hydrogen into helium in his core, radiating light and heat like a cosmic campfire. But like all good things, Bob's hydrogen supply eventually runs out. This is where things start to get interesting. Without hydrogen to fuse, Bob's core loses its primary source of outward pressure. Gravity, which has been patiently waiting for its moment, goes full beast mode. The core begins to collapse under its own weight, heating up and squeezing tighter than a packed subway car during rush hour. At this point, if Bob were a smaller star, he might end his life as a white dwarf or neutron star. But Bob is no lightweight. His core keeps collapsing until it becomes a point of infinite density, a singularity. Imagine trying to stuff an entire elephant into a suitcase. Now imagine that suitcase is smaller than an atom. That's essentially what's happening here. And the results are just as extreme as they sound. While the core collapses, the outer layers of the star don't just sit idly by. They rebel, triggering a massive explosion known as a supernova. This isn't just a fireworks show, it's one of the most powerful events in the universe. For a brief moment, the star shines brighter than an entire galaxy. The shockwave from the explosion hurls the outer layers into space, leaving behind the collapsed core. And if the core is massive enough, at least 3 times the mass of the sun, it doesn't stop collapsing. Instead, it forms a black hole. During the collapse, the core becomes so dense that electrons and protons are forced together, forming neutrons. This process releases an enormous amount of energy, contributing to the supernova explosion. But in a massive enough star, even neutrons can't resist gravity. The core shrinks until it's smaller than a pinhead, and yet it contains the entire mass of the star. At this point, space-time itself gives up trying to keep things normal. The result? A singularity wrapped in an event horizon, the black hole's infamous point of no return. Congratulations! You've just created a black hole. This new cosmic entity is a region of space where gravity is so strong that not even light can escape. It's like the ultimate do not enter sign, except instead of ignoring it, the universe obeys. But wait, there's more. Not all black holes are created equal. Depending on their mass, they can fall into one of three categories. Stellar mass black holes. These are the babies of the black hole family, formed from the collapse of individual stars. Intermediate mass black holes. These are the mysterious middle children, weighing in at hundreds to thousands of solar masses. Supermassive black holes. Found at the centers of galaxies, these monsters weigh millions to billions of times the mass of the Sun. Think of them as the universe's VIPs. Question: can you skip the star? Yes, sort of. While most black holes form from stars, the universe is full of overachievers. Under the right conditions, black holes can form directly from collapsing gas clouds. These are known as direct collapse black holes, and they might explain how supermassive black holes formed in the early universe. It's like baking a cake without bothering to mix the ingredients. You skip a few steps and still end up with something deliciously dense. When a star collapses and decides to become a black hole, it doesn't just let go of all its bad habits, it keeps spinning, and boy, does it spin. Imagine a cosmic ballerina pulling her arms in during a pirouette, except instead of spinning on stage, this ballerina is the size of a star. And instead of applause, she's creating a vortex that warps space and time. Here's the deal. When something as big as a star starts to shrink, it has to conserve its angular momentum. That's just a fancy way of saying what spins keeps spinning. And when all that mass gets compressed into an incredibly tiny space, the spinning ramps up to mind-boggling speeds. How fast, you ask? Try near the speed of light. It's not just fast, it's hold on to your atoms because everything's about to get weird fast. And oh, it gets weirder. This spin doesn't just stop at the black hole itself. No, the black hole is such an overachiever that its rotation literally drags space and time along for the ride. Enter the ergosphere, the cosmic equivalent of a merry-go-round from a nightmare. Normally on a merry-go-round you can jump off when it gets too wild. But in the ergosphere, you're not just spinning around, you are the ride. Space-time itself is swirling like cosmic cotton candy. And you're trapped in the swirl, whether you like it or not. Now let's talk physics fun. The ergosphere isn't just there to mess with you. It's actually got some serious energy to offer. Picture this. You're in the ergosphere, and suddenly, some genius physicist, thanks Roger Penrose, figures out that particles entering the spin zone can split into two. One particle gets flung away with extra energy, and the other gets sucked into the black hole, reducing its spin. It's like robbing the universe's greatest DJ mid-set and walking away with some of their best beats. Oh, and those spectacular jets of energy shooting out of some black holes. Yeah, the ergosphere might be partly to blame for those. It's as if the black hole got so amped up from spinning that it couldn't help but throw a cosmic tantrum, shooting high-energy particles across galaxies like it's trying to say, "Stay away!" or at least send snacks. So next time you think of a black hole, don't picture a boring stationary void. Picture a cosmic whirlwind throwing a never-ending rave, dragging everything nearby into its chaotic dance. It's not just a black hole, it's a spinning, space-time twisting, energy-flinging party in the depths of the universe. Fun fact, not all black holes come from stars. Stellar mass black holes, as dramatic as they are, aren't the only members of the black hole family. Meet their mysterious older cousins, primordial black holes. Unlike their more theatrical relatives, who form from the fiery deaths of massive stars, these black holes were born in the chaotic pressure cooker environment of the early universe. Not long after the Big Bang, and by not long, we mean the universe was barely stretching its legs mere fractions of a second into its existence. Here's the setup. The Big Bang wasn't exactly a calm affair. It was a cosmic explosion of energy, matter, and heat, with everything expanding outward in a roiling, chaotic mess. During these first moments, the universe was so dense and hot that even the laws of physics were still trying to figure themselves out. In this primordial stew, some regions of space became denser than others, like cosmic lumps in an otherwise smooth batter. Now, in a typical universe, if there is such a thing, those lumpy regions might smooth out over time. But in the early universe, where the laws of physics were still throwing curveballs, these dense patches could collapse under their own gravity, squeezing down into impossibly small points. And voila! A primordial black hole was born tiny compared to today's cosmic monsters, but still packing a gravitational punch that could make even the largest stars jealous. The smallest ones wouldn't stick around for long, thanks to a quirky phenomenon called Hawking radiation, where black holes slowly lose energy and evaporate. Tiny primordial black holes would have fizzled out long ago, leaving behind a cosmic trail of subatomic particles. But the larger ones? They could still be lurking out there, hidden in the vastness of space, quietly minding their own gravitational business. And here's where things get really intriguing. Some scientists speculate that primordial black holes could be the answer to one of the biggest mysteries in astrophysics: dark matter. Dark matter is this mysterious, invisible stuff that makes up about 27% of the universe's mass and energy but doesn't interact with light, making it impossible to see. Could primordial black holes be the elusive dark matter we've been searching for? It's a tantalizing idea, but we're not quite there yet. More detective work is needed to crack that cosmic case. But before you start worrying about primordial black holes gobbling up your breakfast or sneaking up on Earth, let's clear the air. They're not exactly on the hunt. These black holes, if they exist, are likely scattered sparsely across the universe, and even the larger ones would be difficult to detect. For all their gravitational might, they're more like the universe's shy cousins, preferring to stay hidden rather than making a splashy appearance. Can black holes keep growing? Absolutely. Black holes are voracious eaters. Once they form, they can grow by gobbling up nearby matter stars, gas, planets, you name it. And if two black holes happen to meet, they can merge to form an even larger one. Think of it like cosmic Pac-Man. Waka waka waka, and before you know it, the black hole has leveled up. So the next time you look up at the night sky, remember, somewhere out there, stars are dying, collapsing, and giving birth to black holes. It's a process that's equal parts tragic, beautiful, and utterly fascinating. And who knows, maybe one day we'll understand these cosmic enigmas even better. Until then, let's just be glad they're out there, and not in our backyard. Let me tell you something wild about black holes. You already know they're the universe's ultimate vacuum cleaners, gobbling up everything: stars, planets, unlucky astronauts. But here's the big question. Can black holes eat each other? Can these cosmic gluttons get even more ambitious and chow down on their own kind? Spoiler alert, the answer is yes. Yeah, you heard that right. When two black holes meet, it's not a polite handshake or a nod of acknowledgement, it's as dramatic as a galactic wrestling match. First, let's set the stage. Black holes form when massive stars die, and their cores collapse under the pull of gravity. What's left behind is a region of space where the gravity is so strong that even light can't escape. Think of black holes as the ultimate cosmic foodies. They consume everything in their vicinity. But unlike your friend who refuses to share fries, black holes don't stop at one meal. They keep growing, getting heavier and hungrier. You might be wondering, how do black holes even meet? Space is, after all, pretty big. It's not like black holes are swiping left and right on some cosmic dating app. The answer lies in galaxy mergers. Galaxies are like cosmic cities, bustling with stars, planets, and yes, black holes. And just like cities expand and change over time, galaxies also grow and sometimes collide. When two galaxies merge, their central black holes get dragged along for the ride, like two heavyweight boxers being pulled into the same ring. The two black holes start orbiting each other, gradually getting closer as they lose energy through gravitational interactions. This process can take millions of years, so don't expect a quick finale. As the two black holes spiral toward each other, they enter a phase called binary black hole dynamics. This is when the real fun begins. They orbit each other at incredible speeds, generating ripples in space-time known as gravitational waves. Gravitational waves are like the universe's way of announcing, hey, something big is happening over here. These waves travel across the cosmos, stretching and squeezing space-time as they go. Scientists on Earth can detect these ripples using instruments like LIGO, Laser Interferometer Gravitational Wave Observatory. It's essentially a cosmic eavesdropping device, allowing us to listen in on black holes' private affairs. Now you might wonder, how does one black hole eat another? Well, technically, black holes don't chew. They merge. And when they merge their event horizons, the boundaries beyond which nothing escapes combine. It's less nom 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 and more. You're now part of me. When two black holes finally collide, it's not a subtle event. Imagine two wrecking balls smashing into each other, but instead of debris, they release an unfathomable amount of energy. This energy is emitted in the form of gravitational waves, which radiate outwards at the speed of light. For a brief moment, the power released by this collision can exceed the combined light output of all the stars in the observable universe. Yes, you read that correctly. All the stars. It's like the universe decided to throw the ultimate fireworks display, and everyone is invited to watch if they have the right instruments. Once the dust settles, or rather the space-time ripples calm down, what's left is a single, larger black hole. This new black hole is more massive than either of the originals, but it's not quite the sum of their masses. Why? Because some of their combined mass was converted into energy and radiated away during the merger. The newly merged black hole then settles down, entering a phase called ring down, where it radiates away any remaining energy and stabilizes. So if you started with a 30 solar mass black hole and a 40 solar mass black hole, the final black hole might weigh only 68 solar masses, with the missing 2 solar masses radiated away as energy. Now let's answer the why. Why do black holes eat each other? The simplest answer is gravity. Black holes are like magnets on steroids. When two of them get close enough, their mutual gravitational pull locks them into a dance that eventually ends in a collision. But there's also a cosmic survival of the fittest aspect to this. Black holes grow by consuming matter, and merging with another black hole is the ultimate power move. Here is a question. How do we even know about black hole mergers? After all, black holes don't exactly send out invitations to their events. The key lies in gravitational waves. In 2015, scientists detected gravitational waves for the first time, confirming a prediction made by Einstein a century earlier. This groundbreaking discovery opened up a whole new way of studying the universe. Since then, dozens of black hole mergers have been observed, providing valuable insights into these cosmic phenomena. What if one black hole decides, you know what, I'm out? Sorry, no such luck. Once two black holes are close enough for their event horizons to overlap, there's no turning back. The event horizon is the point of no return, where gravity becomes so strong that nothing, not even light, can escape. Once two black holes cross this boundary, they're destined to merge. It's like cosmic quicksand. The more you struggle, the faster you sink. Now let's talk about the heavyweights of the black hole world. Supermassive black holes. These giants, found at the centers of galaxies, are millions to billions of times more massive than the Sun. When galaxies merge, their supermassive black holes eventually find each other and begin their gravitational dance. These mergers are even more dramatic, releasing gravitational waves so powerful that they can distort space-time on a galactic scale. Perhaps you're asking yourself, what happens to all the stars and planets when black holes collide? Well, the effects can be both destructive and creative. Some stars get flung out of the galaxy entirely, while others get caught in new orbits. And sometimes, the merger creates shockwaves that trigger the formation of new stars. What happens when three black holes throw a cosmic dance party? Absolute chaos. It's like a soap opera, but with way more drama, and thankfully, no awkward love triangles. When three black holes come together, the universe stages a chaotic gravitational ballet that's as unpredictable as it is mesmerizing. Known as a three-body problem, this cosmic encounter turns the orderly dance of two black holes into a wild, unpredictable tangle. The gravitational forces between the trio are so complex that their orbits become erratic, with each black hole pulling and pushing the others in a gravitational tug-of-war. Sometimes two black holes will form a close binary pair, leaving the third as a bewildered spectator, until it's inevitably flung away at high speeds in what scientists call a gravitational slingshot. In rare cases, all three may merge over time, but more often than not, one gets ejected and banished to roam the cosmos alone while the remaining two settle into a binary system. This cosmic threesome is a reminder that when it comes to black holes, the universe loves a bit of drama and unpredictability. Here's a fun or terrifying fact. Our galaxy, the Milky Way, is on a collision course with the Andromeda Galaxy. In about 4.5 billion years, the two will merge, creating a new galaxy often referred to as Milkomeda. And yes, both galaxies have supermassive black holes at their centers. When they finally collide, it will be the ultimate black hole showdown. Don't worry, though we won't be around to see it. Why this matters? Black hole mergers are more than just cosmic spectacles. They're windows into the fundamental laws of physics. By studying these events, scientists can learn about the nature of gravity, space-time, and even the origins of the universe itself. Plus, let's be honest, they're just plain cool. So, can black holes eat each other? Absolutely. And when they do, it's a spectacle of cosmic proportions. From their slow gravitational dances to their explosive collisions, black hole mergers remind us of the sheer power and beauty of the universe. And who knows? Maybe out there, in some distant galaxy, two black holes are already gearing up for the next big feast. So the next time you see someone at a buffet stacking their plate a little too high, just remember, somewhere in the universe, black holes are doing the same thing on a much grander scale. Hold on to your atoms, folks. Because today, we're embarking on a journey to one of the most bizarre and mind-bending places in the entire cosmos. A black hole. Now, before you grab your space helmet and wonder if there's Wi-Fi at the event horizon, let me warn you. This isn't your average space vacation. Black holes aren't just places. They're cosmic enigmas where the laws of physics as we know them throw up their hands and go, "Yeah, I'm out." First things first, what is a black hole? In simple terms, it's a region in space where gravity has gone absolutely bananas. This is thanks to an enormous amount of matter getting squished down into a ridiculously small volume. Think of compressing the entire Earth into a lima bean. That's the kind of extreme density we're talking about. At this point, gravity becomes so strong that even light, the fastest thing in the universe, can't escape. Hence the name, black hole. It's like the universe's ultimate roach motel. Stuff checks in, but it doesn't check out. Alright, it's time to get up close and personal with the anatomy of a black hole. At the center of a black hole is the singularity, a point so dense and extreme that physics just shrugs and says, "Yeah, I got nothing." Imagine stuffing your entire wardrobe into a tiny suitcase. You jump on it, sit on it, and when the zipper finally gives out, boom! A tear in space-time. That's the singularity. Infinite mass in zero space. No rules, no returns. Next up, the event horizon. The boundary that separates the oops from the oh no. This is the ultimate one-way ticket. Once you cross it, there's no going back. No refunds, no escape routes, and definitely no GPS signal. Think of the event horizon as the edge of a cosmic cliff. From the outside, everything looks calm. But once you step over, boom, you're toast. Or, to be more precise, you're spaghetti. Surrounding the black hole is the accretion disk, a swirling mess of gas, dust, and unlucky stars that got too close. Think of it as the black hole's welcome mat, but instead of greeting you, it grinds everything into oblivion. And don't let the black in the black hole fool you. The accretion disk is a cosmic spotlight. If black holes were introverts, their accretion disks would be the extroverted roommates throwing wild parties. Finally, some black holes just can't contain their excitement or their fury, and they throw out massive jets of high-energy particles. These jets can stretch for light years across space, shooting out at nearly the speed of light. Think of it like a galactic warning sign, do not enter. Or maybe it's more like a cosmic sneeze. If the singularity is the heart of the black hole and the event horizon is the stomach, these jets are its, well, let's just call it a dramatic cosmic exhale. Alright, grab your space snacks and fasten your seatbelts. We're about to take the ultimate cosmic plunge straight into a black hole. What could possibly go wrong? Let's say we're approaching Sagittarius A*, the supermassive black hole at the center of our galaxy. It's about 4 million times the mass of our Sun, and roughly 27,000 light-years away. In human terms, that's far. In cosmic terms, it's just around the corner. As we get closer to the black hole, the universe decides to pull out its bag of party tricks, and trust me, things get really weird. Imagine this. Stars are zooming around the black hole like they're in some cosmic NASCAR race. Except there's no finish line, just endless laps around the ultimate heavyweight champ of gravity. If these stars had headlights, it would look like the world's most chaotic traffic circle. But the real showstopper is something called gravitational lensing. Here's the deal. The black hole's gravity is so ridiculously strong that it doesn't just suck in matter, it bends light. It's like the black hole went to clown school and learned how to turn the fabric of space-time into a funhouse mirror. Picture this. You're looking at a star behind the black hole. Normally you'd think, well, can't see it. There's a giant black hole in the way. Nope. The black hole's gravity bends the light around it so you can actually see the star's light wrapping around like it's on a roller coaster track. And what do you get when light takes a detour like that? Some of the trippiest visuals in the universe. Stars stretch, twist, and sometimes even form perfect rings around the black hole, known as Einstein rings. It's like the universe decided to try on Instagram filters, but instead of vintage or Clarendon, it went with warp reality beyond all recognition. So as you stare out the spaceship window, everything looks warped and wavy. It's dazzling, confusing, and maybe a little nauseating, like watching a Salvador Dali painting come to life. One moment you see a star where it shouldn't be, the next it's doing the cosmic cha-cha, all thanks to the black hole's gravity bending light like it's auditioning for Cirque du Soleil. Funny, right? Until you remember that light itself can't escape this place, and you're heading straight for the source of the chaos. Here's where things take a turn for the dramatic. If you're watching this trip from a safe distance, you'd see something truly bizarre. As our ship approaches the event horizon, time appears to slow down. From your perspective, we're frozen in place, like a celestial freeze frame. But inside the ship, we're doing just fine until we cross the event horizon. Once we're in, there's no going back. Gravity has won. We're officially on a one-way trip to the singularity. Let's not mince words. falling into a black hole is a bad idea. And if you're wondering why, let me introduce you to a delightful concept called spaghettification. Here's how it works. The gravitational pull of a black hole increases dramatically as you get closer to it. Near the event horizon, this difference, called the tidal force, becomes extreme. For example, if you're falling feet first, the black hole's gravity on your feet is much stronger than the gravity on your head. The result? You're stretched out like cosmic taffy. And when I say stretched, I mean stretched. You wouldn't just be elongated, you'd be torn apart atom by atom, your molecules pulled into a stream of particles that spirals into the black hole. It's like the universe's most aggressive Pilates session, except instead of getting more flexible, you're just gone. But here's the twist. Not all black holes are equal when it comes to spaghettification. Small black holes, like those a few times the mass of the sun, are ruthless. Their tidal forces near the event horizon are so intense that spaghettification happens before you even cross the event horizon. Supermassive black holes like Sagittarius A times at the center of our galaxy are more forgiving, at least initially. Their event horizons are farther from the singularity, so the tidal forces are weaker. In theory, you could float past the event horizon of a supermassive black hole without immediately getting stretched into spaghetti. Of course, this just gives you more time to think about the inevitable. If you're wondering whether you'd feel the spaghettification as it happens, the answer is probably not. By the time you notice something's wrong, it'll already be over. Comforting, right? Alright folks, buckle up because we've done it. We've crossed the event horizon. Welcome to the inside of the black hole, where the laws of physics have thrown in the towel, reality is on a coffee break, and frankly, no one knows what's going on. But don't worry, this is an all-inclusive trip to the great unknown. As we plunge deeper, things get weird. First, every direction now points inward. That's right, there's no up, down, or left. It's like your GPS lost its mind and decided that every route leads straight to the singularity. Now speaking of the singularity, our final destination, it's that tiny, terrifying dot at the center of the black hole. Picture this, all the mass of the black hole crammed into a space smaller than a sugar cube. Think of it as the universe's version of an overpacked suitcase, but instead of clothes, it's infinite density. But let's focus on what's around us for now. You might be wondering, what does it look like in here? Excellent question. Nobody knows. Scientists think we might see bizarre, distorted versions of the outside universe. The light from stars behind us could be stretched and smeared, creating a trippy kaleidoscope effect. It's like the black hole decided to open a pop-up art gallery featuring what even is reality. As we approach the singularity, our ship's sensors are going haywire. Some theories say we might hit a quantum Planck star, a bizarre super-dense object that could be the black hole's core. Or maybe we'll slide into a wormhole, a theoretical shortcut to another part of space-time. If that happens, hold tight, we might pop out in another galaxy, another dimension, or even another universe. I hope you pack snacks. Others think the singularity might be a gateway to a baby universe. Yep, falling into this black hole could mean becoming part of the Big Bang for a brand new cosmos. Congratulations, you're the godparent of a fledgling universe. Of course, there's always the less glamorous possibility. We get squished into oblivion and cease to exist. But hey, who's thinking about that right now? So as we drift closer to the singularity, enjoy the ride. This is a once-in-a-lifetime trip. Literally, you can't come back. Inside a black hole, it's less about the destination and more about the journey through chaos, warped space-time, and mind-bending possibilities. Would you like a souvenir? Too bad the black hole keeps everything. So, what did we learn from our trip to the black hole? For starters, black holes are far more than just cosmic vacuum cleaners. They're extreme, fascinating, and dare I say it, beautiful. They challenge our understanding of physics and the universe itself. Oh, and if you're planning a visit, pack light, avoid the spaghettification zone, and don't forget to marvel at the accretion disk on your way in. Because while a trip to a black hole might not end well, it's sure to be the ride of a lifetime, quite literally. Here's the deal. We're about to visit one of the scariest, strangest places in the universe, a neutron star. These spinning cosmic lighthouses are the leftovers of massive stars that couldn't quite commit to becoming black holes. It's not like a theme park ride. It's more like stepping into the universe's ultimate nope zone. Forget about roller coasters or skydiving. This journey will make you appreciate how good you've got it on Earth. Oh, and try not to lose your atoms on the way. First, what's a neutron star? Okay, quick science briefing. A neutron star is what's left behind when a massive star, one many times the size of our sun, goes supernova. After the star explodes, the core collapses under gravity. But it doesn't stop there. Oh no! Gravity keeps squishing and squishing until the protons and electrons in the atoms are forced together, leaving behind a ball of, you guessed it, neutrons. However, because it doesn't have enough mass to become a black hole, it stops just short of that ultimate transformation, settling instead for being one of the densest objects in the universe. Imagine taking the entire mass of the sun and squeezing it into a sphere about 12 miles across. That's smaller than most cities, but with more mass than you can wrap your head around. It's like turning Mount Everest into a sugar cube, but way more intense. Now, pulsars are the cool kids of the neutron star club. These stellar remnants spin incredibly fast, like a cosmic fidget spinner on steroids. Some of them rotate hundreds of times per second, emitting beams of radiation from their magnetic poles. From Earth, these beams look like flashes of light, kind of like a lighthouse, but way more intimidating and definitely not something you'd want to navigate toward. So where do we start our journey? Well, imagine we have a spaceship capable of defying the laws of physics, shrugging off gravity, and giving us a front row seat to one of these spinning marvels. Neutron stars aren't exactly the friendly neighborhood type. They're scattered across the cosmos, often lurking in supernova remnants where they were born. As we approach our chosen pulsar, let's talk about the environment. The area around a neutron star isn't your typical space backdrop. It's extreme. The gravity is so intense that if you weighed, say, 150 pounds on Earth, you'd weigh about 1 billion tons near a neutron star. Your shoes would never forgive you. The gravity of a neutron star is so strong that if you were to drop a marshmallow onto its surface, the resulting explosion would be equivalent to a small nuke. So, maybe leave the snacks behind. The gravity around starts to ramp up. And by ramp up, I mean it's about to go full Hulk mode on us. Oh, and did I mention the magnetic fields? Neutron stars have magnetic fields that are quadrillions of times stronger than Earth's. The closer we get, the more intense things become. If you brought a credit card with you, the magnetic strip would be wiped clean in an instant. But hey, who needs cash in space, right? More importantly, this magnetic field supercharges particles in the surrounding space, creating streams of radiation that can fry pretty much anything that gets too close. It's like standing in front of the universe's biggest microwave, but instead of popcorn, you're the snack. And if you're wearing anything metallic, well, let's just say it'll be the last time you see it, or yourself. Now let's admire the pulsar's rotation. Picture this, a sphere spinning hundreds of times per second. The energy of that spin powers those beams of radiation we talked about earlier. As the pulsar rotates, these beams sweep across space, creating a pulse every time one of them points in our direction. That's why we call them pulsars. If our spaceship had a radio receiver, we'd hear these pulses as regular rhythmic signals, a kind of cosmic heartbeat. But wait, it gets weirder. Some pulsars have companions. These are binary systems where the pulsar orbits a regular star, a white dwarf, or even another neutron star. If we're lucky, we might witness a cosmic tango where the pulsar's gravity siphons material from its partner, creating an accretion disk, a swirling, glowing ring of hot plasma. It's chaotic, beautiful, and just a little horrifying. For argument's sake, let's assume we have some sci-fi level tech to protect us. As we descend towards the surface, things start to get weird. First, there's the light. Neutron stars can emit beams of electromagnetic radiation. And if you're unlucky enough to be in the way of one of these beams, congratulations, you've just been microwaved. Then there's the time distortion. Remember Einstein's theory of relativity? Well, here's your chance to experience it firsthand. The intense gravity bends space-time so much that time itself slows down. To someone watching from a distance, you'd appear to be moving in slow motion, like an astronaut in a low-budget sci-fi movie. Landing on a neutron star is, well, impossible. But hypothetically, if you could, you'd be greeted by a crust so dense and unyielding that it makes diamonds look like marshmallows. The surface is made of nuclear pasta. Yes, nuclear pasta. It's not spaghetti or penne, but the matter here forms structures that scientists have whimsically named lasagna, gnocchi, and fusilli. This is the densest and strongest material known in the universe. Dropping a pebble on this surface would release as much energy as an atomic bomb. So, no skipping rocks here. And if that's not enough, it's hotter than 1,000 suns. Literally. Temperatures can reach up to 1,000,000 degrees Kelvin. And under that crust, a soup of neutrons. It's like the universe's most extreme pressure cooker. Scientists aren't entirely sure what's going on down there, but it might involve quarks, the building blocks of protons and neutrons, swimming around like cosmic goldfish. Ah yes, the classic spaghettification. You've heard of it in black holes, but neutron stars can dish out a similar fate. If you get too close, the gravitational difference between your head and your feet would stretch you out like taffy. Not the fun kind of taffy, though. More like the ouch, my atoms are screaming kind. As we orbit the pulsar, we might also notice something unusual. Gravitational waves. If the pulsar has an irregular shape or is part of a binary system, it could send ripples through spacetime itself. These waves are faint, but we've actually detected them from neutron star collisions here on Earth. It's like the universe is whispering its secrets through the fabric of reality. Oh, you thought pulsars were done showing off? Not even close. These cosmic oddballs sometimes have partners, because apparently even dead stars don't like being alone. So here's the deal. Some pulsars are part of binary systems. This means they're paired up with another celestial object, like a regular star, a white dwarf, or even another neutron star. Now, when a pulsar and its companion get a little too close, the drama begins. The pulsar's intense gravity starts to pull material away from its partner. It's like a cosmic pickpocket, but instead of stealing wallets, it's grabbing entire streams of gas and dust. This stolen material doesn't just float around aimlessly. No, it spirals into an accretion disk, a glowing, swirling ring of superheated plasma that forms around the pulsar. Picture a cosmic donut, but one that's millions of degrees hot, and definitely not edible. As the accretion disk forms, things get messy. The material in the disk is whipped around at incredible speeds, generating massive amounts of heat and energy. It's chaotic, beautiful, and just a little terrifying, like watching a blender on full speed, but the blender is powered by physics gone wild. And if you thought that was the end of the show, think again. As the pulsar keeps siphoning material, it can sometimes emit bursts of X-rays or gamma rays. That's right, this cosmic thief announces its heist with a literal fireworks display. But wait, the pulsar isn't just pulling material for fun. Oh no, it's actually fattening itself up. The more material it siphons, the more massive it gets. In some cases, this can even cause the pulsar to spin faster, turning it into what scientists call a millisecond pulsar. A neutron star spinning so ridiculously fast it makes a fidget spinner look lazy. And let's not forget about the companion. This poor star is getting torn apart in real time. Its outer layers being stripped away by the pulsar's relentless gravity. If the companion happens to be another neutron star, things can escalate even further. The two stars might eventually spiral into each other, creating a collision so violent it sends gravitational waves rippling across the universe. It's the ultimate breakup story, literally tearing space and time apart. So, in summary, a pulsar with a companion is like the most dysfunctional relationship you can imagine. One partner is stealing everything, the other is falling apart, and a chaotic, plasma-filled spectacle lights the whole thing up. It's messy, it's dramatic, And it's a reminder that even in space, relationships can be complicated, like a man who gives his all, loses everything, and is left watching the woman he loved walk away, shining brighter without him while he's left spinning in chaos. I think we've had enough of these neutron stars for now, massive spinning corpses of once glorious stars. They pulse, steal, and light up the cosmos with relentless drama. Let's step back before the universe's wildest heartbreaks pull us in too deep. If you'll excuse me, I need to go decompress, preferably somewhere far, far away from gravity this intense.